The second law of thermodynamics. The word thermodynamics was coined in 1840 from the Greek roots therm, which means heat, and dynamics, which means power. So this is a branch of physics that deals with heat, work, and their relations with energy, entropy, and properties of matter and radiation. There are four basic laws in thermodynamics. The zeroth law of thermodynamics. So if we have a system A, which is in thermal equilibrium with system C, and we have another system B, which is also in thermal equilibrium with system C, then systems A and B are in thermal equilibrium with respect to each other. This law basically emphasizes on the fact that there has to be a temperature difference between two systems for heat transfer to take place between them. The first law of thermodynamics says that energy can be converted from one form to another, but it can neither be created nor destroyed. This means that the energy of the universe is constant. Second law of thermodynamics. The entropy of the entire universe as an isolated system will always increase over time. So, here in this mathematical expression, S stands for entropy, and delta S basically means the change in entropy. So delta S unif means that the change in entropy of the universe is always more than or equal to zero. Entropy basically, in a very crude sense, measures the randomness of a system, how disordered the system is, and it tells us how dispersed the energy of the system is. So if we have a system in an initial configuration, as time passes, the system will tend to that configuration in which the energy of the system is maximally spread out. Alright, so the second law of thermodynamics governs the direction of process in the universe. So the spontaneous processes, that is the processes that occur on their own, they tend to a direction towards thermal equilibrium. And if the spontaneous process is reversible, the entropy of the system in that case would be constant. But if the spontaneous process is irreversible, then the entropy of the system in that case will always increase over time. The third law of thermodynamics states that the entropy of a perfect crystalline structure at absolute zero temperature is equal to zero. So we will be focusing only on the second law of thermodynamics. Let's talk about the history of the second law of thermodynamics. In 1854, Rudolf Clausius stated that heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. So what he implies here is that heat can never flow spontaneously from a colder object to a hotter object. And this is in line with the second law of thermodynamics because it gives the direction of a spontaneous process. And when we do the mathematics, we see that in a spontaneous process where heat is flowing from a hot object to a cold object, the entropy is increasing. Lord Kelvin and Max Planck gave their individual statements, and both their statements were combined to give one common statement, which is called the Kelvin-Planck statement, which states that it is impossible to devise a cyclically operating device, the sole effect of which is to absorb energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work. So what this means is that in any machine that we have manufactured and are using, we can never convert the entire heat energy into equivalent amount of work. So heat energy will never be entirely converted into mechanical energy. There will always be some loss of heat energy, which we can never use. So this means that there is no machine in the entire universe which is 100% efficient. There are limits to the efficiency of the machine. So this is a very interesting prediction about the ultimate fate of the universe. It is called the heat death of the universe, and it is based on the second law of thermodynamics. So we saw that any isolated system, it will tend towards thermal equilibrium as time passes. So this is applied to the universe as a whole. We treat it as an isolated system and say that as time passes, and like lots and lots of time passes, there will be no temperature difference between any two objects in the universe. That is, the universe will be in thermal equilibrium. there will be uniform temperature everywhere, and energy will be distributed evenly throughout the universe. And because there is no temperature difference, no work can be extracted from this isolated system, which in our case is the universe. That means all life forms, machines, all activities will cease to exist because there will be just no change. So this is basically based on the possibility of the system going to a disordered state, which is the highest in the case of spontaneous processes. In spontaneous processes, there is also the possibility of the system going into a highly ordered state. Although the possibility is extremely low, but still it is non-zero. So scientists also predict that it may happen at one instant of time where everything might go back into order and the life cycle of the universe might restart.
Hello everyone, I will be demonstrating the second law of thermodynamics. For this, I will be using a plastic box, a piece of paper and some thermocol balls. I will use this paper as a partition to divide the box into two equal halves. Like this. Now, I will put the balls in one half of the box. So this is my system in its initial state, in which the balls are in one half of the box only and the other half of the box is empty. Now, watch what happens when I remove this partition. So when I remove this partition, the balls tend to move to the other half of the box. This is a spontaneous process, that is, it happens entirely on its own. As time passes, the balls will try to distribute themselves evenly throughout the whole box. Why does this happen? So when the system was in its initial ordered state, that time the balls were concentrated in one half of the box and the energy of the system was concentrated in that region. As the system evolves with time, the balls tend to move to the other half of the box so that the system's energy is much more dispersed, and in the final state, the system is going to be in a disordered state. That is, entropy of the system will increase. One more thing, no matter how much time passes, the balls will never on their own go to one half of the box. Theoretically, it is possible, but the possibility is very, very, very low. That means the system will never on its own go from a disordered state to an ordered state. Yes, if I apply an external force, I can push the balls to one half of the box in this manner. So you might think that now the system has gone from a disordered state to an ordered state. So has the entropy decreased? The answer is no, because when I'm applying an external force, I am providing energy to the system and doing work on the system. Therefore, the net entropy of the system increases. Thank you.
To understand center of gravity, we need to know the difference between mass and weight. Mass is a fixed quantity. It is the amount of matter present in a substance, and it does not change throughout the universe. Weight depends on the gravitational field in which the object is situated. So in the case of Earth, weight of the object is the Earth's gravitational force acting on the object through the object center of gravity. Center of gravity is an imaginary point around which the weight of the object is symmetrically distributed. Similarly, center of mass is an imaginary point around which the mass of the object is symmetrically distributed. And in the case of a uniform gravitational field, center of gravity and center of mass coincide.
Now I will demonstrate the concept of center of gravity. For this, I'm going to use a hammer, a box which has been asymmetrically cut from the top side, a black sketch pen, a rubber band, and a wooden scale. So a scale is a measuring device which measures the length of an object. For this reason, manufacturers ensure that the mass of the scale is evenly distributed along its length. Therefore, the center of gravity of this scale will lie at its geometrical center. Since this is a scale of 30 centimeters, I have drawn this point of center of gravity at 15 centimeters. Okay, and around this point, mass is symmetrically distributed here, here, as also here and here. Okay, now I will try to balance this scale using my finger. If I place my finger here, the scale is not going to be balanced and it's going to fall down. Okay, similarly here. But when I place my finger under the center of gravity, the scale is now balanced. So the Earth's gravitational force is acting on the center of gravity in the downwards direction, and my finger is providing a normal force in the upward direction. These two forces balance each other out, and therefore my scale is balanced. Now coming to this box was initially a parallelepiped. That means this entire thing was complete and it is hollow from inside. So because it is a three-dimensional object, its center of gravity will lie somewhere inside. But for demonstration purposes, I am going to show its center of gravity on the surface. So this was its center of gravity initially. Now I chipped this side and kept this part and kept it aside, and therefore this side has lesser material compared to the lower side. So the center of gravity shifts downwards towards the side where there is more material. Okay, so the center of gravity was initially here and now it is approximately somewhere here. So this is the center of gravity of this asymmetrical object right now. This point right here. Alright, now I will try to balance this box on this narrow base. Our intuition tells us that the box will not be balanced on it. So let's see. So as you all saw, our intuition is correct and the box falls over. Now why does this happen? I will extend this point. I will draw a line through this point in the vertically downwards direction. Like this. So this line is called the line of gravity. It is an imaginary line which is drawn from the center of gravity of the object. Just a minute. We had considered this point as the center of gravity of our object. So it has to be drawn from the center of gravity of the object. So just a minute. Alright, now it's correct. Alright. So this line which is drawn from the center of gravity of this object till it's an imaginary line which is extended till the center of the earth, because it is the earth's gravitational pull force that is pulling the object downwards towards its center. So this line of gravity, as you can see, it is not passing through the narrow base. It is passing outside the base. Therefore, when we try to balance the object on this narrow base, the object falls. Okay. Now I will extend this line in the opposite direction. Okay. Now, when I try to balance this box like this, you can see that the box is staying stable. This is because the line of gravity is now passing through the base. Therefore, the box is stable. Now, I will draw a line perpendicular to this first line. And it will be perpendicular to the first line and it will pass through the center of gravity of the object. Okay. So, okay. So here is my line which is passing through the center of gravity and it is perpendicular to this line. So when I place my box like this, naturally this position is more stable as compared to the previous position. Now why is that so? Here also the line of gravity is passing through this big base, correct? And here also it is passing through the big base, right? But out here the center of gravity, okay, out here the center of gravity is closer to the surface as compared to this position where the center of gravity is a little bit higher from the surface. So there are two things that we have to keep in mind. One is that the center of gravity, the line passing through the center of gravity, the line of gravity should pass through the base, and second, the center of gravity should be as close to the ground as possible. Now let's take the wooden scale again. I wish to balance the scale on this edge by placing it on the table like this. So it's obviously not going to stay here. That is because the center of gravity of the scale is here and there is nothing to support it below it. Therefore, it's not going to stay here. But now, if I attach a heavy weight, in our case, the hammer, with the help of a rubber band, let's see what happens. Please be careful while doing this. As you can see, with the help of the hammer, I am able to balance the scale on this edge of the scale. How does this happen? So the center of gravity of the scale, which was initially at its geometrical center, has now shifted outside the scale towards the heavy weight. So the center of gravity is not a fixed point. We can change its position by attaching different weights. And also the center of gravity is lying below the base. This is the base on which we are balancing the scale, but the center of gravity is lying below it. Even then, this structure is balanced because the line of gravity is passing through this portion of the hammer and down towards the center of the earth. So this is our balance system. In human beings, the center of gravity is usually 1 inch below the navel spot. That is somewhere around here. For people who are muscular and heavily built in the upper portion of their body, their center of gravity is slightly above this point, that is closer to the heavier part of the body. And for people whose lower portion of the body is heavier, their center of gravity is slightly lower, that is closer to the heavier part of their body. Now, as you all can see, I am standing on my 2 feet and I am stable. This is because the line of gravity is passing through my center of gravity to the center of the earth through the base. The base in this case are my 2 feet and the space between them. And therefore, I am stable. If I wish to balance my body on 1 foot, let's say the right foot, watch how my body moves. So as you can see, my body shifted to the right hand side so that the body weight is balanced by my right foot. Also, my center of gravity has slightly shifted towards the right and the line of gravity is now passing from the center of gravity to the center of the earth through my right foot. That is, it is passing through the base and therefore I am balanced.
Now, I will be demonstrating the concept of acoustic dampening. For this, I am going to be using a cardboard hollow cylindrical tube, a source of sound, a platform on which to place the source of sound, a plastic lid, a metallic lid, and cotton. So in the experiment, I'm going to be placing the source of sound at one end of the tube, and I'm going to take a little bit of cotton, insert it at this end, so that the maximum energy of sound waves are directed inside the tube. Some of the sound energy will be absorbed by the cotton that I have inserted, and very little energy will be allowed to escape to the surroundings. At the other end of the tube, I will be placing different materials to explain the concept of acoustic dampening, and the listener will also be keeping his ear at the other end of the tube. Now, since the tube isn't very long and I'm not placing the material within the tube, I'm placing it at the end of the tube. So it is advised for this experiment that the listener should be as close to this end as possible. So when we will be performing the experiment, the camera phone will be very close to the end of the tube. Let's begin with the experiment.
I hope that it was evident from the experiment that there was a variation in the intensity of sound heard when I placed different materials at the end of the tube. So, the first material, that is the plastic, when I place the plastic at the end of the tube and I start the sound from here, the sound waves travel through the vibrations of the air molecules within the tube, and when the sound wave energy is incident on the plastic being little hard and dense, that is the molecules of the plastic are closer together, therefore the incident energy on the plastic, that energy, most of it is transmitted, some of it is reflected, and little is absorbed by this plastic material. Therefore, there wasn't much difference in the intensity of sound heard at this end where the plastic was compared to when there was no plastic. The second material that I placed was cotton. Now, cotton is highly fibrous and porous. So, when I place cotton at one end of the tube and start the sound from here, the sound waves travel through the tube, they are incident on this cotton, and most of the sound wave incident energy is absorbed by the cotton, some of it is transmitted, and very less is reflected back by the cotton. Therefore, the sound that was heard when I placed cotton, it was significantly damped compared to when there was no cotton. Now, the energy that the cotton absorbs, part of it is converted into thermal energy of the cotton molecules, and the remaining part of it goes into the vibrational energy of the air molecules which are trapped within this cotton material because it is fibrous and porous. In the third case, we observed significant dampening. So there was maximum dampening in the case of metal. Why does this happen? When I place the metal here at the end of the tube and start my sound from here, the sound waves travel through the tube, they are incident on this metal. Metal being highly dense, it reflects most of the sound wave energy back. Some of it is transmitted and some is absorbed by this metallic lid. Alright, so therefore we observe that different materials have different dampening capacities, and that is why we heard this variation in the sound. Obviously, the maximum sound was heard when there was no material placed here. That is, when the sound waves were traveling through the tube, through the vibration of the air molecules, and there was nothing placed here. That means there was air here. There is air here. Correct? One more parameter to be considered here is the thickness of the absorbing material. Ideally, a material of infinite thickness will be the perfect absorber, as all the sound wave energy incident on it will be absorbed by it. But that is not the case in reality. So therefore, we say that the more the thickness of the material, more will be the sound energy absorbed by it, and that much more acoustic dampening will occur. Thank you.
Acoustic dampening finds its applications in situations where the noise or any unnecessary sound has to be removed or minimized. So for example, in a recording studio, as you all can see, the walls surrounding the mic are made up of a particular type of structure. That is, the walls have a certain texture and they may be made up of a material so that the entire combination is such that the absorption of sound waves energy has improved, and whatever the person is recording on the mic, the quality of that person's sound is enhanced. Also, in theaters, we have carpets and curtains which are made up of extremely thick and dense materials so that whatever is being played on the speakers is heard clearly till the last row in the theater.